I heard that some of it's that everybody uses their phone as a hotspot, and hotspots can definitely mess around with the bandwidth a little bit. It was always really annoying to try to get stuff in the gym just because students would be using their phones as hotspots. So really quick, now we're kind of sharing this with YouTube Live. I wanted to show you the data that I collected on Friday from that terrible, terrible experiment. So here's all the data that I entered in. I had one data, like basically one participant that was a majority of zeros. And so, and I think that was because of technical difficulties. So because of that, I kind of left that data out. So here we have the data from 9 people. Thank you so much for those of you who turned it in. So here is our average for whole report. And you can see that most people are getting about 4 items, give or take, from the entire array. Now, when we look at the partial report, most people are getting between 1 and 2. So you can kind of see here our averages, like the minimum is a little less than 1, the maximum is basically 2.5. So here's what's really interesting. So when Sperling kind of looked at this data, and I kind of talked about this on a little section about short-term memory that I recorded on Friday afternoon, and I believe I sent you an email about that on Saturday. So Sperling basically multiplied the partial report by 3. And the reason that he chose to do that is because you didn't know what row you were going to get ahead of time. And because you didn't know what row you were going to get, he had to make the assumption that at least the entire array or some portion of it had to be available at that point. And so when you multiply our data, so if you multiply the average of partial report by 3, that means that in addition to the 1.6 items, give or take, that you remembered from the proper row, Sperling would have said that there were probably about 3 or 4 other items in the array that you would have known, but because we didn't cue you on it, you couldn't answer for them. So in this case, your partial report is actually a little bit better than your whole report. Now, if we delayed that cue a little bit later, these would be about even. Your whole report would look no better than partial reports. So I feel pretty good about the data. They look like the kind of stuff that you would actually find with Sperling. So yeah, I collected that for you, and I took a look at the averages this morning just to kind of see what was going on. So because we spent a lot of time talking about doing that demonstration, we didn't have a lot of time to talk about working memory. So hopefully you've taken some time, and if you haven't done it yet, make sure that you do it. I posted it on YouTube. You can listen to it anytime that you want. And you actually get to see me without a mask, which I know, shocking, she looks like that. You may have forgotten what my lower half of my face looked like. But I kind of worked through some of the basics of the model of memory that we're kind of working from. And I do talk a bit about sensory memory, and I briefly started talking about short-term memory. So the last place that I kind of left off is that with short-term memory, we have really small capacity limits. So I want to be clear about the difference in capacity limits between sensory memory compared to short-term memory. So sensory memory, the capacity is large, very, very large. But the duration is very, very short. I believe in the case of visual sensory memory, its duration is about maybe 300 milliseconds. For speech or auditory materials, it's actually closer to about 2 seconds. Now, short-term memory is different. It is limited in duration. It's probably not going to last longer than a few minutes, if even that. But what's especially notable about short-term memory is its capacity limits. And back in 1956, I kind of talk about this in the video, George Miller proposed that he found this kind of curious phenomenon where when he looked at short-term memory tasks, or as they're sometimes called, immediate memory. When he did these different immediate memory tasks, what he ended up finding is that across a wide variety of tasks, about 5 to 9 items were recalled every time. And not only did he find this in memory tasks, he also found this in what we call absolute judgment tasks. So I tried to describe it in the video, but now that I'm in front of a blackboard, it might actually work a little bit better to show you what an absolute judgment task is. So I'm going to go ahead and stop, and I'm going to pin myself so that I can make sure that you can all see me. So an absolute judgment task is kind of something like this. So here, I kind of create a test line. So we're going to call that our test. And then maybe I have 3 different lines that I have to basically choose from. So an absolute judgment task is kind of something like this. Let me see if I can move that out for you. So the idea is that I have a test line, and then I have 3 different lines that I basically can choose from as options. And so the idea is, which one of these best matches the test line? Is it A, B, or C? Now, the correct answer is pretty close to B, or at least I meant to draw it that way. But one of the things that Miller kind of reported is that generally people are really good at this task, but they tend to kind of max out at about 7 items, give or take. So here. And one more. So now I've got 7 different options, and all of a sudden the task becomes much, much harder. So when I have 7 options that I have to basically judge against this test line, the task becomes much, much more difficult. So one of the things that's actually kind of interesting about Miller's findings is that he kind of thought that this 7-item limit thing was probably just a coincidence. As it turns out, it's not just a coincidence. We do tend to find a 7-item limit in a lot of different things. So Miller's paper is famously titled The Magical Number 7 Plus or Minus 2. If you're interested in accessing it, you can find it online, and I'm happy to send you a copy. But there are some issues with this. So really quick. Now, if you've had me for general psychology, you probably know what I'm about to ask you. I need somebody to help me. I need somebody who really loves Disney to help me. So that can be somebody here in class, or this can be somebody on Zoom. I need a volunteer who is good at Disney. And if you're on Zoom, you are going to have to turn your mic on for this. I'm sorry. It won't work without it. Would anybody like to give this a try? Avriana, you want to do it? Okay. So Avriana is going to demonstrate this for us, and now if you're not able to hear, that's okay. I'll kind of describe what's happening after it does. Avriana, here's what I'd like you to do. I'd like you to name all 7 dwarves from Snow White and the 7 Dwarves, if you would, please. All of them. All of them. Do it.
Okay, so Dopey, and then there's like Sneezy, I think, something like that. And Grumpy,
Okay.
Sleepy,
Okay.
I don't remember this.
Okay. Does anybody else want to try? Robin? Okay.
Dopey, Grumpy, Dog, an angry one.
Mm-hmm.
Is there a shy one?
Mm-hmm.
Or something like, no,
Mhm.
that's a buddy. Pascal.
Mm-hmm.
That's all I know.
Okay, so so it's okay if you didn't get them all. That's okay. What I'm more interested in is less that you got them all than what you did in terms of your recall. So here's something that's kind of interesting. If you had all 7 items in your short-term memory, so your short-term memory is what you are basically paying attention to right now. It's in your mind. If you had all 7 dwarves, so I noticed 2 things about both of your recall. And for those of you that are trying this in your dorm or you're on Zoom, you can try this with yourself. Pay attention to whether or not there's a long pause after you recall about the 3rd or the 4th item, because that's what a lot of people do. Avriana did it, Robin did it. There were pauses in between between each of the items that you recalled, but generally after people recall about 3 or 4 of them, it turns out that most people take a long pause in between the 4th and the 5th item, or the 3rd and the 4th item. And the reasoning is, if all 7 items are in short-term memory, why do you need to take that pause? Why do you need to grab the rest of those items from long-term memory if you can hold 7 items? And it's because of that that a lot of people actually really think that this 7-item limit was an overestimation, that it's actually probably closer to about 3 or 4 items that we can hold in short-term memory at once. But one of the things that we tend to find is that you can actually, so here's the bad news. So I'm going to start with some bad news. You cannot change your short-term memory capacity. Not really. Your short-term memory is inherently tied to attention. You can't pay attention to too many things at once. And as a result, you can't really have a very large short-term memory capacity. So that's the bad news. The good news is that you can utilize a strategy known as chunking to help you. And a lot of more recent short-term memory and working memory researchers have actually said that it's not that memory is limited to 7 items, but rather that our memory span is limited by the number of different chunks or groups that we can hold. So chunking is basically when we group items together into a smaller number of meaningful segments. So for example, right here on the screen, we are looking at a long string of letters. There's 9 of them. That is almost to your maximum short-term memory capacity limit, at least in terms of Miller. But hopefully you'll notice that these are acronyms. So UFO, IBM, and TNT. If you have prior knowledge of these acronyms, it is not actually 9 items that you have to remember. Rather, it's about 3 chunks, 1 for UFO, 1 for IBM, and 1 for TNT. And it turns out that research by Donald Broadbent in 1975 and Cowan in a huge paper in 2001, which interestingly enough was cutely titled The Magical Number 4 ± 1, basically said that Miller's original item limit was an overestimation, that our short-term memory, rather than being limited between 5 and 9 items, is actually closer to being limited to 3 to 4 items or chunks, and that's it. Now, occasionally I will get somebody who tells me, oh, so that's why phone numbers are 7 digits, right? No, phone numbers existed before somebody had reported the 7-item limit. I would also add, it is not 7 digits that you're remembering in a phone number, it's 2 chunks. It's a group of 3 and a group of 4, and then if you add an area code, that's another group. So when we prevent strategies, we tend to find that our short-term memory limit is closer to about 3 to 4 items. And we find this not only in verbal materials, we also find this in visual materials as well. When you prevent people from using higher order strategies like chunking, the limit's about 3 to 4. So I'm going to read 3 consonants. If you are doing this in Zoom, please, if you're doing this in Zoom, you may count backwards from 3s silently. So I'm going to read 3 consonants to you right now. I want you to try to remember them for later. J, R, C. Now I'd like you to count backwards from 3s, starting at 341 and go. Okay, and stop. What were the consonants I gave you? JRC. So if you got that, very good. Is there anybody who only remembered a couple of those? Okay, we're going to do another one. Okay. Okay, your consonants are M, T, P. Now I'd like you to count backwards from 3s from 288 and go. And stop. What were the consonants I gave you? MTP, good job. Okay, final one. Okay, so the final one, here are your consonants, F, W, N. I'd like you to count backwards from 3s by 640 and go. And stop. What were they? Okay, now that one was probably the easiest one, yes, FWN. So what I just did with you is actually kind of a demonstration of a study known as the Brown-Peterson task. And I gotta say, every time I do this demonstration, I wonder why the class's data does not look like the Brown-Peterson data. And I think maybe I'm just doing something wrong, or maybe there's more to the experiment than I thought. So in the Brown-Peterson task, the participants in this study, and this is back in the 50s, basically were given the task that I just gave you. They had to remember some consonants. Odds are pretty good. They probably had more consonants to remember than just the 3 I gave you. And then they had a period where they had to count backwards. And that duration could last as few as 3 seconds, all the way up to 18 seconds. In one case, I actually gave you up to about 30 seconds. But in this task by Peterson and later with Brown-Peterson actually finds that short-term memory has a very short duration. In fact, noticing kind of this nice smooth curve over the delay. So within 3 seconds, most people are getting these items correct. That is almost cut in half, 3 seconds later. By 9 seconds, only about 20% of the information was retained, and it basically kind of bottoms out by about 18 seconds. So what this tells us about short-term memory is that it has a very small, limited capacity, and it also has a very short duration. So one of the things that I mentioned last time, there's this idea that short-term memory is a passive buffer. So the idea is that short-term memory is basically functioning as kind of a halfway storage system, a temporary storage system. So it's kind of like creating a temporary internet file or a cookie or something like that. So the idea here is that items are only going to be temporarily stored, which means one of two things is going to happen as a result. It's either going to go into long-term memory and be there forever, or it's going to basically be lost forever at some point once it leaves short-term memory. So this means that information will either be lost or forgotten, or it has to be transferred somewhere else. All right, everybody good? But here's kind of a problem with that, and we'll kind of talk about this in a minute. So within the next 10 to 15 years after Miller's paper, we are kind of getting the idea that short-term memory, we can actually modify information in short-term memory, which means it's not the passive buffer that we've been led to believe. So you do not need to know this for any test. I'm mostly just showing this to you because there are some different ideas about the architecture of memory. And this is one of those models. So this actually comes from my doctoral advisor. I call it the fried egg model. You can kind of see why I call it the fried egg model, because there's fried egg right there. So this is an embedded processes model of working memory. And I'm not going to test you on this model at all, but I just kind of want to show that depending on who you talk to, some people believe that this distinction between short-term memory and long-term memory is not super duper clear cut. Rather, a model like this actually assumes that short-term memory is just a temporary activation of information that's stored in long-term memory. So one of the things that the multi-store model of memory doesn't really talk about is how information go from long-term memory into short-term memory. So here's kind of an example of that. Can y'all think about your most recent birthday? Now, so here's the thing. I have just temporarily activated that for you. So it was in your long-term memory. You weren't really thinking about it until I prompted it. And at that point, it's gained access to short-term memory because short-term memory is what you're currently paying attention to right now. So short-term memory is either going to be made up of a temporary activation of information that you've already stored away, or it's information from your sensory stores accessing short-term memory, as we saw in the multi-store model. So this model by Cowan, so here's long-term memory, and then there's activated memory, which is our short-term store. And you can kind of see, so this is activated memory. And then here's what's really critical for that activation is attention. You need to be paying attention to it in some way. And in fact, you can actually see that a subset of that short-term memory is an area called the focus of attention. Now, the focus of attention, according to this model, is incredibly limited. Some people say it's only limited to one item. I've done research showing that under certain cases, it can be bigger. But this is just one other way to kind of think about memory and to think about how it all connects to each other. And now you can say you've seen a fried egg model. So now we're going to talk a little bit about working memory. Okay. So is short-term memory, the way that we've conceived of it prior to the development of working memory, useful? People like to say that it helps us with phone numbers, but I mean, how many of us even do that now? Think about it. When somebody gives you a phone number, what do you do with it? You put it in your phone. There are very few phone numbers that I remember from people these days. Like, I remember my partner's number because I have to write it on all of my emergency contact forms. I know my mom's number. I know the phone numbers of my grandparents because they have landlines and I've been calling those landlines for years. But beyond that, like my friends, do I know Dr. Roy's phone number? No. I just put her name in my phone and it calls. So short-term memory used to be able to help out with that, but now we don't really need it for those things. Baddeley and Hitch in 1974 found that you tend to use it a lot more than you think. It's not just for remembering phone numbers. It's not just for remembering items that you're trying to remember to get at the store. It's not remembering what you had for breakfast yesterday, because that's long-term memory anyway. But you use your short-term memory and your working memory more often than you think. So I kind of mentioned in the hashtag what working memory paper that I had you read last week, that the person who wrote the paper, Nelson Cowan, is probably in the top 3 working memory people. Alan Baddeley is #1, and I'm going to share something really embarrassing with y'all. So my first year of grad school, I had only been in graduate school for maybe about 3 months. And I went to my very first graduate conference in Toronto. And I remember I was at a working memory session in Toronto and I was sitting like 2 rows behind Alan Baddeley. And I was just like this. I was standing and fangirling over working memory researchers. And then you realize they're just like normal people. All right. So think about this, for example, mental arithmetic. Can somebody try this for me? Can somebody multiply 12 times 14 in their head right now? Somebody want to try that for me? And what do you get? In your head, don't use paper or a calculator. That's cheating. Huh? 184? Nope. 12 times 14. Yes. Okay, so who was that? I couldn't hear. Okay, Emma. So I want you to tell me a little bit about how you actually ended up doing that. So first, what did you do?
I know that 12 times 12 is 144.
Okay.
And then I added 12 to 156, and I added 12 to 156.
So basically, this was a multi-step process. Yeah. So first you got your 144, and then you held on to that. You kept it in your short-term memory. And then what did you do to it? You added additional information to it. So here's the thing. If short-term memory is just a temporary buffer, you shouldn't be able to do any of that at all. You basically held on to something in short-term memory and you changed it, you manipulated it, you updated it. Prior to 1974, conceptions of short-term memory were basically, you can't do anything with them. If it's in short-term memory, you can't do anything with it. It's a buffer. Baddely says, Alan Baddely and Graham Hitch say that you can manipulate things in short-term memory. You can modify things. You can update things. You can substitute things. Your short-term memory is not just a passive little buffer. So this is where we get to working memory. This is what I study, folks. Admittedly, it is not the most sexy of topics, but you use it all the time. So working memory is a system that allows information to briefly be held in mind. And I know what you're thinking. Well, Dr. Gilchrist, how is that any different from short-term memory? Wait, it allows for both the temporary storage and also the processing of materials. So not only can you store information in working memory, you can also process that information. And so oftentimes, if you're talking to a working memory researcher, they're not going to call it short-term memory. They're going to call it working memory. I tend to use them interchangeably, but it's okay if you don't. Now, if you tell me you think working memory is not real, well, then I'll just make a face, but you're allowed to think that too. I am kidding. Okay. So this is the original model. So the original model was developed in 1974, Baddely updated it again in 2000. Here's another embarrassing thing about your instructor. When I was in college, I definitely remember going to a Chinese buffet with my college boyfriend because I was just learning about this stuff. And I may have made a model of this on my plate with lo mein because I'm a dork. But this is kind of the model, and we're going to talk about each of these in detail. So we have 3 major subsystems, and then we have an overseeing component. So we have our central executive. Our central executive is largely designed to oversee all of working memory and the 3 different subsystems that we are going to talk about. So first, and probably the one that we know the best, is the phonological loop. This is a part of working memory that holds information in a speech-based code. So it's all based on speech. It's based on verbal materials. On the other side, we have what is called the visuospatial sketchpad. This is for spatial processing and visual information. Now, I want to be clear on what I mean by visual information. I mean things like patterns. I mean things that do not have a very strong verbal component. So spatial processing, patterns, and things like that. And then finally, our 3rd subsystem that was added in 2000 is the episodic buffer. The episodic buffer is really important for integrating information. It also serves as an interface between short-term memory and long-term memory. So when I asked you to think about your last birthday and you were able to bring that into your conscious awareness, it's the episodic buffer that is what allows you to do that. It also is really critical for helping remember things like narratives and plots to your favorite movies and time-based information and things like that. And you can take my word for it. I had to read the original Baddely and Hitch paper for my comps. There's like 9 different experiments in there. Actually, there might be closer to 12. It was a very long paper. All right, everybody good? Okay, so the central oh, you need me to go back, Adriana? I'm sorry. I will take a sip of my Dr. G fuel. It's been forever since I've seen this in a can. And yes, I do recycle, in case some of you were wondering. I would also advise you, if you are sharing information about working memory with other people, do not make my mistake and make a model out of lo mein on your plate. Right, you good? Okay, so the central executive is the most important part. It has a very limited capacity, and it does tend to resemble attention in a lot of ways. It tends to be involved with, a lot of complex tasks. So it oversees working memory by and large. So if you've ever heard the term executive function, this is partially where that idea comes from. So if we're talking about updating information, if we're talking about monitoring information, that is something that the central executive is largely going to be in charge of. Now, here are two major important assumptions. So one major assumption of this model, and I'm going to write this down, it's a really important term when we talk about working memory and the different components. So there are two major assumptions with Baddeley and HITCH'S model of working memory. So first of all, if you have two tasks that both draw on the same component, so if they both draw on the phonological loop, or if they both draw on the episodic buffer, or if they both draw on the visuospatial sketchpad, you can't perform them at the same time. You can't. On the other hand, if two tasks use different components of working memory, you can perform them well together or separately. So if one task uses the visuospatial sketchpad and the other uses the phonological loop, you can actually do both of those at the exact same time. This is a pretty important principle when we talk about working memory. And for those of you that are zooming in, I'm going to show you this term. I have written it down. I'd encourage you to write it down. This is what is referred to as selective interference. So the idea here is that object or tasks that involve both the visuospatial sketchpad, if they're both doing that, you can't do them at the same time. On the other hand, if you can do two tasks at the same time, the idea is that they must be drawing on different processes. If you can't do them at the same time, they must be drawing on, if you can't do them at the same time, they're both drawing on that same process. We don't necessarily have to know what that process is, but the logic is if you can't do them, they're both drawing on similar processes. Okay. Now, here's some evidence of this, and this comes from Robbins and colleagues back in 1996. So, by the way, I should kind of mention that especially as we move on in cognitive psychology, you're going to hear me talk a lot about chess. And so these researchers were interested in the working memory processes that are involved in playing chess. Now, obviously, you might think that there's a very strong visual component, in which case there is, but perhaps there are other components going on as well. So they looked at weaker, more novice chess players, and they looked at stronger chess players, people who'd been playing for a while, possibly even people who were grandmasters. Now, here's what's really interesting. While they had these players, so these players were expected to play chess, and they were rated on the quality of the moves they made and their accuracy and their performance. So while they're playing chess, they have to do a few possible different tasks. So they could just tap, which is kind of functioning as a control task. You can tap and play chess at the same time, right? It doesn't take a lot of work. But the other tasks that they were told to do the same time that they were playing chess tapped different portions of the working memory system. So they either had to randomly generate different numbers, so they had to basically create a random number sequence. That is very largely a central executive task. Their central executive task was random number generation. They had to, if they weren't doing that, they had to press keys in a specified order, which is largely a pattern and thus is a visuospatial sketchpad task, or they had to repeat a word over and over again, which is basically a phonological loop task. And we'll talk about why on Wednesday. So they either had a control task, a central executive task, a visuospatial sketchpad task, or a phonological loop task. Now, the logic behind this is that if their performance gets worse on chess while they're doing one of these tasks, that means that that component of working memory is critical for playing chess. So we would probably say that there's probably some visuospatial sketchpad involved, right? Maybe some central executive as well, because playing chess requires a lot of careful thought and planning and organization. Well, it turns out it depends on your chess skills. So here's what they find. So here are our weaker chess players in green. Here's the quality of their chess move selection. Lower numbers mean worse performance. Now, in general, our weaker chess players are really bad. But they tend to be worse for tasks that involve the visuospatial sketchpad or that random number generation. And it turns out that even with our stronger chess players, that same result happens. They do really well in the control task. If they have to repeat a word over and over, they do fine. But if they have to tap in a pattern, or if they have to randomly generate numbers, their performance plummets. So what this tells us is that regardless of whether you are a new chess player or a very seasoned, experienced chess player, playing chess seems to rely on two different components of working memory. It relies on the central executive to engage in planning and strategy and making proper moves. And it also requires visuospatial processing so that you can think through different attacks, different defenses, and placement of pieces on the board. So players rely more on the visuospatial sketchpad and the central executive when they play chess. We know this because by the principle of selective interference, their performance is worse when they engage in these concurrent tasks. And additionally, it doesn't matter whether you're a novice or you're an expert, you use working memory similarly. So I think that's neat. I also suck at chess. I tried to learn how to play a couple of years ago, and I'm not very good at it. Like my partner keeps telling me, just use chess.com. I'm like, but they don't explain why this is a bad move. I like checkers. Like it's just wrong that pieces can move multiple squares at a time. It's just weird to me. Okay, one more slide and then we'll call it a day. So we're going to start by talking about the phonological loop. So the phonological loop is largely based on speech-based code. So this means that anytime that you're reading something, as you're reading these slides right now, you're using your phonological loop. You just don't always realize it. So your phonological loop is based on two different components. We have something called a phonological store, so a storage area where auditory words are stored. And then we also have what is called an articulatory control process, which is signified by this curvy arrow. So the idea is that items gain access to the phonological store, but the phonological store is kind of limited in how long it can stay active. It only can really hold about 2 seconds worth of information. Hey, that's pretty similar to our auditory sensory memory now, isn't it? So this can only really hold about 2 seconds worth of information unless you rehearse it via the articulatory control process. So that's what happens for auditory words. You also do this with visual words, but here's what's really critical. And we'll talk about this next time with a class demonstration. With our articulatory control process, if information is presented to us visually, like it is with these slides, the articulatory control process basically translates visual information into a verbal code so it can then be stored. So it basically, the articulatory control process translates information for us, and it also offsets decay and loss of information in the phonological store. We'll talk some more about the phonological loop next time. I hope you are all having a wonderful day today. I hope you enjoy the rest of your day. I will send you a link to the YouTube video once it's done processing. Do not forget selective interference, and I will see you next time. Bye, everybody.